So here's a huge question. How do you build a thinking machine? I mean, really think about it. You'd probably imagine something incredibly complex, right? Something almost magical. But what if you don't start there? What if you start with something, well, simple, like really simple? Something that can have just one tiny thought, a single yes or no. That idea, that one simple decision, that's where the entire story of modern AI really kicks off. And at the heart of that origin story is our main character today, a model called the Perceptron. Think of it as a simple little brain that could, but as we'll see, also couldn't. It had so much promise, but it was hiding this one fatal flaw that ended up derailing the entire field of AI for more than a decade. All right, so here's the plan. We're going to meet this simple brain, see what it could do, and then hit the wall, the one problem it just couldn't crack. From there, we'll dive into how that single failure led to the infamous AI winter, what breakthrough finally brought the spring, and how all of this, believe it or not, became the bedrock for all the AI we see today. Let's get into it. Okay, first things first, let's meet our star, the very first artificial neuron. So this is the perceptron. You'll also hear it called a binary threshold unit, or BTU. And the concept is just beautifully simple. Just think of it like a little bouncer at a club. It checks a few IDs, the yes or no evidence, decides how much weight to give each one, and then makes the final call. You're in or you're out. A simple yes or no. And here's how that little thought actually happens. It's a four-step dance. First, it just gathers up its inputs, which are nothing more than zeros and ones. Simple. Second, it weighs them. Some inputs are more important than others, so an input with a high weight is a big deal, while one with a low weight is meh, not so much. Third, it just adds up all those weighted inputs and compares the total to some internal line in the sand, a threshold. And finally, the decision. If the total sum crosses that line, it fires off a 1, that's a yes. If it doesn't, it just stays quiet and outputs a 0, a no. That's literally it, the whole process. I know what you're thinking. That sounds way too simple to do anything useful, right? But you'd be surprised. That tiny little mechanism is powerful enough to learn some of the most basic rules of logic itself. And what's cool is how this mimics simple decisions you see all over nature. Let's take an analogy. Picture a bird that's super picky. It will only eat berries that are both round and purple. So when it sees a berry, its little bird brain is essentially asking two questions. Is it round? And is it purple? It's only going to eat if the answer to both is a big yes. That right there is a classic logical AND gate. And here's the kicker. A single perceptron can learn to do this perfectly. You just tweak its weights and its threshold, and you can get it to fire that 1 only when both inputs are 1. Just like the bird. It totally nails the AND gate. And it could learn other stuff too, like or, eat if it's round or purple, and even not. This was a massive deal at the time. People thought, this is it, we found the atom of intelligence. So why can it solve these specific problems? Well, it all boils down to this one super important property. A property that is both its greatest strength and its greatest weakness. These problems are what's known in the biz as linearly separable. Linearly separable? What on earth does that mean? It's actually a really simple visual idea. Imagine you plot out all the possible answers on a graph. If you can take a ruler and draw one single straight line that puts all the yes answers on one side and all the no answers on the other, boom, it's linearly separable. And for problems like and, or, and not, you can always do it, no problem. But that single straight line, its superpower, that was also its kryptonite, its fatal flaw. Because it turned out there was one little logic puzzle, a puzzle that seemed just as simple as the others, that a perceptron absolutely positively could not solve. And this just shows it perfectly. Take a look at the AND problem on the left. Easy, right? You can draw a diagonal line and separate the 1 yes from the 3 no's. But now, look at the puzzle on the right. This is XOR, or exclusive OR. It means you want one or the other, but not both. See how the yes answers are now kitty corner from each other? Now you try it. Pause and try to draw one single straight line to separate the yeses from the nos. Yeah, you can't do it. It's literally impossible. And this wasn't just, oh, we haven't found the right settings yet. No, the math proved it was a fundamental contradiction. For a perceptron to solve XOR, one of its internal numbers would have to be, at the exact same time, both bigger than a value and less than or equal to that same value. That's a paradox. It makes no sense. The simple brain hit a wall. It was broken. So who cares about one little logic puzzle, right? Well, it turns out everyone did. This one tiny abstract problem had huge real-world consequences. It basically plunged the entire super promising field of AI into a deep, deep freeze. See, back in the early 60s, the hype was off the charts. People were saying the Perceptron would soon be able to tell the difference between a tank and a tree from a photo. But then, in 1969, two guys named Minsky and Papert dropped a bomb, their book, Perceptrons. It just laid out the cold, hard math, showing everything the Perceptron couldn't do, with XOR as the star example. And the fallout was brutal. People took it way too far, assuming that if the Perceptron was flawed, then all neural networks must be a dead end. Research funding just vanished. Labs closed their doors. For nearly 15 years, progress stalled. They called it the AI winter. But winter doesn't last forever, and eventually, a thaw began. The breakthrough that changed everything wasn't about building a better perceptron. It was about using the ones we already had in a completely different way. And here was the aha moment. The solution wasn't a better, smarter neuron. It was a team of them, a network. So check this out. Instead of just one, you use layers. Imagine the first layer, the hidden layer, is a team of specialists. Each little perceptron in that layer is trained to spot just one simple pattern, like an AND gate or an OR gate. Then you have a second layer with a single perceptron that acts like the manager. This manager doesn't look at the original problem at all. It just asks the specialists in the first layer, hey, what did you guys find? Based on their reports, it makes the final call. And with this team-based approach, this layered structure, you're no longer stuck with straight lines. You can draw complex, curvy decision boundaries. You can solve any logical problem. And yes, that includes the once impossible XOR. So this brings us full circle, the legacy of the perceptron. How could its big, embarrassing failure actually be one of the most important moments in the history of AI? Well, because that failure forced everyone to understand the limits of a single neuron. I mean, think about it. For a simple problem with just 2 inputs, there are 16 possible logical rules you could make. A single perceptron can handle 14 of them. That's pretty good. The only 2 it chokes on are XOR and its opposite, XNOR. But that's where things get crazy. Scale it up just a little bit. With just 6 inputs, the number of possible logical functions explodes to over 18 quintillion. That is a number with 18 zeros. That's the giant bar you see on the left. And the number of those that a single perceptron can solve, that's the bar on the right. You can't even see it. It's not a sliver, it's a statistical ghost. It's a rounding error. And this just hammered home a crucial point. The real world is almost never simple enough to be solved with a single straight line. And that is the big takeaway. The perceptron failing to solve XOR wasn't the end. It was the beginning. It was the roadblock that forced researchers to discover the highway. It taught us the most important lesson in all of AI. To build a powerful mind, you don't need a perfect genius neuron. You need a network, a team of simple neurons all working together. Every single piece of modern AI you've ever heard of, from ChatGPT to the art generators, it's all built on that one fundamental idea. The power isn't in the neuron, it's in the network. So it kind of makes you wonder, doesn't it? What other simple ideas are we playing with right now? Ideas that maybe seem limited or have their own fatal flaws that are secretly the building blocks for the biggest technologies of tomorrow.